Hello everyone, we are George Charitos, Srinidhi Srinivasan and Aditya Bagri, and welcome to our YouTube video for the Big Data Analytics project. Our project was Traffic Violations Analysis and Prediction. It was part of Big Data Analytics class here in Columbia University. We selected a traffic violation analysis and prediction because traffic violations are a universal issue. It exists everywhere, in all countries of the world, and still there has been no solid solution for it. Also in the United States, it exists on a large scale since automobiles are the #1 means of transportation. Furthermore, we want to make our streets safer. Our goal is at first stage to analyze traffic violations from 2012 to 2015 in the state of New York. Track down interesting results like top violation types, age versus violations, gender versus violations, etc. Moreover, we want to use prediction algorithms to predict future violation results and thus suggest prevention measures for the state of New York. The most integral part of a big data analytics project is always the dataset. We selected as basis of our project the New York State dataset, which is 1.5 gigabyte roughly. It includes traffic violations in the state of New York from 2012 to 2015, and the columns include violation charge code, violation description, violation year, violation month, violation day of week, age of violation, gender, state of license, police agency, court, and source. As far as the system design is concerned, initially the dataset was fed to our big data processing engine, preferably from a distributed file system like HDFS. Then we executed the analysis part using query language to output results, visualize them, and proceed to prevention suggestions. Finally, using our dataset and insightful queries, we run prediction algorithms. The big data processing engine we used is Apache Spark. Spark is the fastest engine for large-scale data processing. It runs 100 times faster than Hadoop MapReduce in memory. It utilizes Java, Scala, Python, and R for writing applications. Also, it includes SQL, data frame, and machine learning MLlib libraries. It can run on Hadoop, Cassandra, Mesos, or standalone, and last but not least, it is open source. The basic operation of Spark is defined by resilient distributed datasets, RDDs. RDDs are Spark's main programming abstraction. They represent a collection of items distributed across many compute nodes that can be manipulated in parallel. The driver program, which is Spark's high-level entity, can launch various operations on these RDDs using different machines on different ranges of the RDD. If, for example, we were to load our dataset on an RDD, Spark's driver program would split it into smaller subsets and assign an executor working on a task for each subset. The programming language we decided to use for our project is Python through PySpark module. We selected Python mainly due to its high level and general purpose. Plus, we feel that Python is more widely used lately and is also the most trending language. To manipulate our dataset and run queries for the analysis part, we use Spark SQL's module. Spark SQL is a Spark module for structured data processing. Unlike the basic Spark RDD API, the interfaces provided by Spark SQL provide Spark with more information about the structure of both the data and the computation being performed. Internally, Spark SQL uses this extra information to perform extra optimizations. There are several ways to interact with Spark SQL, including SQL and the dataset API. When computing a result, the same execution engine is used, independent of which API language you are using to express the computation. This unification basically means that developers can easily switch back and forth between different APIs based on which provides the most natural way to express a given transformation. Finally, to visualize our queries and results, we utilize Python's Matplotlib library for pie charts, bar charts, and different types of graphs. As we stated earlier, the analysis part of our project includes running insightful queries on our dataset and visualizing the results. We use SQL modules and Matplotlib library. Initially, we want to create a data frame of our dataset in Spark. The create_dataframe.py file of our code first imports the PySpark.sql data context. Next, it loads our dataset to Spark RDD while mapping the columns of the CSV dataset with the comma separation splitting. Finally, it converts the RDD to a data frame by executing rdf.show. We can see our data frame here. The first dive into our dataset we think should be to figure out the percentage each age contributes to our dataset. In other words, to plot the number of violations versus the age of the violator. The code is located in age.py. First, we want to plot a bar chart of 6 age sets of 10 years each, starting from 16 to 75. After running filter and count operations on our dataset, we divided each count by the total number of violations to find the percentage. Next, we plot the bar chart here. It becomes clear in this bar chart that younger ages contribute to more than 60% of the total violations. To get a better picture, we will plot a graph of distinct ages versus number of violations. We need to create a data frame with first column the age is ascending, and second column the frequency each age appears in the dataset. For that reason, we use rollup and flat map operations, and we create the age df data frame. Then we also create a list for the 2 columns and we plot the result. Notice here in the graph that peak of the curve at 23 years old. Also notice how steep the graph is rising and how steep the fall of the curve becomes. To better analyze this result, it's important to dive into the age of 23 years old and analyze the top violation types in it. That way, basically, we can see what that curve is mainly consisted of. File age 23 top 5 violations.py has the relevant code. It follows the same procedure as the ladder graph, but instead it uses a data frame only for age 23 and roll-up and flat map operations for the violation description column. As you can see here, the bar chart speeding is by far the most frequent violation. In addition, all the rest of the violations here are labeled as aggressive driving violations. Moving to gender type queries in the gender pie_chart.py file, we use simple filter and operation to plot a pie chart for the gender of the violator. In the pie chart, it becomes clear that male motorists actually get the lion's share of the violations. Another interesting query has to do with mobile phone usage while driving. This violation or dataset is labeled as operating MV mobile phone. In the phone violations.py file, by first filtering our dataset for that violation, we create a phone DF data frame. Next, we split this data frame into 4 distinct ones, one for each year, 2012 to 2015. Using filter rollup and count operations for the age at violation column, we get a data frame with columns, with 2 columns, one with ascending age 16 to 95, and the second with the number of operating MV mobile phone violations that this age had in that specific year. Next, we created a list for the X and Y axis and plot the results. The results are quite unexpected. One would think that with the rise of smartphone usage and messenger type applications, the amount of operating MV mobile phone violations would increase through the years. Instead, it decreases from 2012 to 2015 by almost 40%. So doing some research into that matter, we found out that in 2010, the state of New York increased fines related to mobile phone usage by almost 50%. That would explain that decrease of this type of violation, as you can see here in the graph. As far as the state license plate is concerned, we tried to look into any inconsistencies concerning the license plate on the state of the violator. We started with a state.py file. Again, by using flat map rollup and count operations, we plot the pie chart. As expected here, New York State has a vast majority of them. We'd like to explore though what is happening in the rest of the states, here in the blue part of the pie chart. We plotted the bar chart here of that 13%. If we look closely, it becomes apparent that most states in the top 10 are states adjacent or in the vicinity of the state of New York, except for the state of Florida. It does not make any sense for the state of Florida to take that much part in traffic violations in New York. One could argue that this is a big state with population of almost 19 million people, while the population of Connecticut, which is a few miles away from New York City, is just 3.6 million. If true, the same should apply for the state of Texas, which is a much bigger state than Florida, with population of 25 million. But it does not. Texas hardly has the percentage of Florida. Given the current data set, it's hard to dive into this inconsistency. Our data set does not include a lot of information, as we stated earlier, but yeah, another data set could definitely enlighten us. This part will be considered as future work. In addition, we extracted some time-related results, such as comparison between years 2012 to 2015. We can see here a month bar chart and day of week bar chart. The years.py plots a bar chart for the years 2012-2015. No significant difference can be seen between each distinct year. In our opinion, this is not a positive result. Traffic violations should be decreasing through the years. New transportation technologies constantly arise, safer roads pop up, automobile safety innovation trending, so the total number of violations should be decreasing. Similar picture you can find in the months.py file concerning month versus violation number. As far as days of week are concerned, we see an escalation from Monday to Friday. Then it becomes apparent that violations have decreased during the weekend, and especially on Sunday, during which many people here in the US stay home. It also makes perfect sense since on a Saturday and especially on a Sunday there's hardly any traffic in the streets of New York. Finally, it's quite interesting to see the top 10 violation types from 2012 to 2015. Top 10 violations.py file is using roll-up count and flat map operation of the violation description time column to plot the results. Again, aggressive driving violations, and you can see get top positions in this bar chart. So, what results do we have up until now? Aggressive driving behavior is evident in our results. We believe this must get the state of New York to a lot of internal conversation. It is a clear sign that there is an absence of proper driving behavior. It is natural to get a ticket for reasons like illegal parking. It does not illustrate aggressiveness. However, speeding, disobeying traffic devices, operating mobile phone, and unlicensed operator illustrate motorist indifference and disregard for other citizens. Also, we notice that the percentage of younger ages into this data set the percentage is too high for that. That's another thing for the state of New York to be concerned about.
Okay, now we will look at Seaborn visualizations. Seaborn is a Python library which is built on top of Matplotlib, and it is used for insightful, actionable data that we can see from our dataset analysis and help in our visualization of the computation for the different fields of the data. Now, Seaborn is a Python visualization library which provides a high interface for drawing attractive statistical graphs that provide actionable insights into the dataset and its computation, and it also has a various number of plots and graphs that we can use for the computation. The first one that we will look at is called the LM-plot, which shows the results of a linear regression within each dataset. As you can see below, I have plotted the age of visualization violation versus the violation year, which is basically the age at which the violator was when they caused the violation. And as you can see, for the different years 2012, 13 and 14, we have a randomly distributed age at visualization for the different parts of the year, and we can see that as we go higher, the plots become fewer and fewer. Now we can use the same plot to also break out the age of the violator in the form of different genders. So here we can see a random distribution of the males and females that also depict their age versus the year at which they caused the violation. Now the other plot that we will look at is box plot. This is an interesting graph because this shows us, by the virtue of height of the box, the age at which the violator was versus the violation day of the week. Here we have an interesting visualization because we can see that for the weekends, which is Friday and Saturday, the height of the box plot or the level at which it is much lower compared to on a Tuesday or a Thursday or Monday, which indicates that youngsters cause traffic violations during the weekend. And this can also be broken out by gender, as can be seen here. Here we see that there is a large difference in the gender ratio on a Tuesday, where females were at a younger age sort of causing the violation versus the males, and this is opposed to on a Sunday, where the two ages are pretty much aligned. We will see this again in the later slides for a different plot. Moving on to the violin plot. Here we have created a combination of the violin plot and the swarm plot, which basically maps the age of the visualization versus the visualization day of the week. And in this case, we look at the thickness of the violin as opposed to the height of the violin. And so, as referencing our previous theory, we can see that the thickness of the violin is the most at a younger age, approximately 23 years old, on a Friday or a Saturday, as opposed to a Wednesday or a Monday. And this reconfirms our theory that the youngsters cause traffic violations on weekends. And again, this can be broken out by gender. And now we are not looking at height, we are looking at the thickness of the plot. And as we saw earlier, the Sunday on a Sunday, the age at violation for males and females was pretty much the same, and this can be confirmed in this graph, as opposed to a Tuesday, where the two thicknesses are pretty different.
Integral part of big data analytics is running machine learning algorithms on a dataset. The basic algorithm categories are classification, clustering, and recommendation. Classification algorithms are relevant to our project. We use them to do multiple predictions. PySpark MLlib modules were selected. The first algorithm we implemented is binary decision tree. It is a BDD-based classification algorithm. It takes as an input the number of variables and the number of possible values each variable can have, and creates a decision tree. Initially, we created a binary decision tree algorithm to predict the gender of the violation given the year of violation, the violation month, and violation day of week. We will predict the gender given these three columns. In predictGender.py, first we import the decision tree module, and then we create an RDD of our dataset. In order to do a decision tree algorithm, we first need to encode our variables and their values. This is because BDDs take only numerical values. We use label point module from MLlib to create that encoding. Our goal is, for example, a row in the if a row in the columns of interest is violation year 2012, violation month equals 3, which is March, violation day of week is Wednesday, and gender equals male, then the label point should be 0 and as the first element, and the list, which includes the three given columns that we have, is 0, 2, and 3. That way, we create the encoding for all other different values of that variable. We basically encoded years 2012 to 2015 to 0 to 3, months January to December to 0 to 11, days Monday to Sunday from 0 to 6, and gender 0 to 2. Next, we create a Python function, gender encode, that serves as an encoder for each row of the BDD. By calling gender label points RDD equals dataset RDD.map gender encode, we create an RDD with rows as labeled points with only the columns of interest. The above labeled point includes a float number as the first element and the list of float numbers as a second. The first element is the column we wish to predict, and the second element is the column we will use to predict the first element. After creating the gender label points RDD, we split the RDD into training set RDD and testing set RDD. We choose the training set to be 70% of random rows of our data set, and then testing set, we choose it here, you can see, to be 30% of random rows. After splitting our data set, we train our decision tree model. Since we have three possible outcomes for the gender, the number of classes is set to 3. After training our model, we create an RDD with only the features, columns, year, month, day, and then we create an RDD with the predictions from the previous one with gender predictions RDD. We also create the gender truth and predictions RDD with 2 columns, one for true value of the gender, one of the predicted value of the gender. So the final step is to calculate the accuracy of the predictor by checking each row of the gender truth and predictions RDD for equivalent elements. Finally, we print the result for the accuracy in the decision tree model. Our predictor has an accuracy of 72%. Now, the next predictor we built is used to predict the age of the violator. We again use the decision tree, and the code can be found in predictAge.py file. Given the year of violation, violation month, violation day of week, and gender, we wish to predict the age of violation this time. The code has the same flow as the gender predictor. The encoding function is slightly different, since in this case, the first label point element, which is what we want to predict, is the age, and also the second label point element is a list that includes year, month, day, and gender. Our first attempt was unsuccessful due to the huge number of classes. More specifically, the possible age values we can find in our dataset extend from 16 years old to 95 years old. By encoding the age as 16 to 95, by the encoding age as 1695 to 0 to 79, we get 80 distinct values, meaning the number of classes must be 80. Unfortunately, MLlib library decision tree can support maximum number of classes 2 to the 5th, which is 32. Our solution to this problem is to use age sets instead of distinct age values. We split the age in 16 sets of 5 years each. Starting from 16 years old, yes, we get the sets of 16 to 20, 21, 25, etc., and encode them into 0, 1, until 15, respectively. This way we reduce our number of classes from 80 to 2 to the 4th, which is 16. The accuracy of the age predictor is 20%. Obviously, it's better than a random selection between 16 different sets. However, it is an inaccurate predictor. It basically tells us that there is no solid connection between the given columns and the column we wish to predict. The age at violation has very little dependency to year of violation, violation month, violation day of week, and gender. In order to confirm that suspicion, we built another age predictor, but this time we used our analysis results. We illustrated previously how the age versus the number of violations behaves. It is clear that the age set of 21 to 25 contains a large portion of the total number of violations. By filtering our dataset RDD, we obtained an RDD with age at violation between 21 and 25 years old. The age encoder was slightly modified to support 5 age values instead of 16. The decision tree model has now 5 classes. Everything else stays the same as in the previous predictor. Now, the accuracy we obtained is 21%. This basically confirms our previous suspicion that the year of violation, the violation month, and the violation day of week and gender columns do not govern at significant extent the age at violation column.
Now we look into various other prediction models. The first one we are going to see is the linear SVM. Linear support vector machine is a very popular method in machine learning and data mining. It is usually used in large data classification. This model is basically formulated as a convex optimization problem. The task of this model is finding a minimizer of a convex optimization function f. The function f has 2 different parts to it. The regularizer part controls the complexity of the model. Linear SVM uses L2 regularization. Also, there is a loss function, which is a convex function in terms of the weight vector W. Linear SVM supports only binary classification with L2 regularization with SGD optimization. Now this is the code of the linear SVM model we have created. Basically, we are going to predict the gender. So there's a gender decode part, as you would have seen in the binary decision tree, in which you decode the data from the data set. So you decode the year, the day of the week, and the gender. Since it's a binary classification, you see that there is only two values, 0 or 1, assigned to it. Now we read the data, and it's filtered and it's parsed through the gender decode, the defined code over here. Then the model is trained using the SVM with SGD program given. Then the training error is calculated through this. The model is trained with an iteration of 100. Now we look at a demo of the linear SVM model. Here is the demo of the linear SVM model. The program is going to be run through Spark Summit. Programs written in Python. Now the file starts to execute. It takes about half an hour for it to complete. So we are not going to show the complete video. Now let's look at the results. Now we look at the output. So we find that the training error is approximately 27%. So the accuracy can be determined as 73%. Now, as I told earlier, we are predicting the gender. Now you might see that the amount of male, the gender classification can be, male would be around 70-75%. So you see the accuracy analogous to that number. This is mainly because the data is extremely random. There is no interdependence between the features we are extracting, which are the years, the day of the week, and the month. Now let's go to the next model. This is the random forest regression. The random forest is a popular regression method. It's an ensemble of decision trees. This model combines many decision trees to reduce the risk of overfitting. The random forest regression is used in this project as a multi-class classification, and the data features we are using are continuous. Random forest trains a set of decision trees separately so that the training can be done in parallel. By combining the predictions from each tree, the variance of the prediction is reduced to improve the performance on the test data. The predictions are combined by averaging the real prediction value of each and every tree. The label which is predicted is the average of the tree predictions. Now this is the code of the random forest regression model for predicting the years. So as you see over here, we parse the data and the label point which is created has a value 0. So this is the label. Since the first field in our data set is the years, it's gonna predict for the years. Then it's trained through a trained regressor model. The number of trees we use over here is 40, and the maximum depth of each and every tree is 2. Then the model predicts based on the test data, which was split, which is the 20% of the complete data set, and then the MSE, the mean squared error, is calculated by this formula. Now, as I told earlier, there are 40 trees and the depth of each and every tree is 2. we find that the mean squared error is approximately 1.23. Since we have used 40 number of trees, there are a large number of trees to predict the years. So you find that the mean squared error has been very low comparatively. Now we'll create a model for predicting the age. So as you see over here, the labeled point, the label is going to be the value 2, which is the third field, which is the age field. Then the remaining two fields, year and month, are given as features. Now data is again split into 80% as training data set and 20% for the test data set. The random forest is trained with 2 number of trees and the depth is 4. We choose this because we'll have 2 power 4 leaves, which is 16, and the feature which is going to be used to predict the age is going to be the months, value 1. So we are having 12 months, so 2 power 4, 16. Again, the data is predicted, and then the prediction is mapped and the labels are created, and then the mean squared error is calculated with the same formula as before. Now this is the output we get. So this is one snippet, which is the second tree over here, and the mean square error you find is 185.9. You find that this is it's huge compared to the prediction of the years. The reason being, there is a high MSE, that is the mean square error, due to randomized data, and also this mean square error can be reduced by increasing the number of trees as well. Next, we will look at the next model. Now we are going to look at the next model, which is the linear regression. Linear regression is a common formulation for regression problems. The model is designed with a squared loss with loss function as given below. Linear regression uses no regularization but uses an SGD optimization as explained in linear SVM model. This is the code snippet. So the data is loaded and parsed over here. Then there is a linear regression model which is trained with the parsed data over an iteration of 100, and the step size is this. Next, the value is predicted using the model.predict over here, and then the mean squared error is calculated. The mean square error was found to be 4.5 million. It's very high. As explained earlier, this MSE is so high due to its random nature of the data. The next model we look at is the logistic regression. Logistic regression is a commonly used model for binary classification. Given a data set and the data points denoted by X over here, the logistic regression model makes predictions based on the following logistic function. The loss function, which is known as the logistic loss, is given by the following formula. The logistic regression uses a LBFGS optimization. It's the limited memory Broyden-Fletcher-Goldfarb-Shano optimization over an SGD optimization because of the faster convergence when using an LBFGS optimization. This optimization requires binary values for the labeled points. So this is the code snippet. Again, the data is loaded and parsed here. Then this is the model. So we are training with the model logistic regression with LBFGS, and the parsed data is trained, and you are calculating the training error. However, there is an error which states that is exceeding the number of inputs in the data set as given here. This is because, as I told earlier, LBFGS optimization models requires a binary value for the label points. So this model is not suitable. We can manipulate this to work for gender as male or anything else, or give it some binary values as we had done in the same case as SVM, but the model becomes exactly the same and it's not unique in nature. Now we look at the naive Bayes classification model. Naive Bayes is a simple multi-class classification algorithm which assumes independence between every pair of features. Now, as we have seen earlier, since the data is extremely random with no interdependence, this model will be useful in making some meaningful predictions with the available data set. Within a single pass into the training data, the model computes the conditional probability distribution of each feature given the label. After this, the Bayes theorem is used to compute the conditional probability distribution of the label given an observation. Now this can be used to make the predictions. In this project, a multinomial naive Bayes is used for the classification. In the classification, each observation is a document and each feature represents terms whose value is the frequency of the term. This model takes an RDD of the labeled point and an optional smoothing parameter lambda as input. This data is first loaded and parsed and then split into the training and the test data sets. The training data set is 60% of the original data set. After the model is trained using this function, the model is evaluated using the testing data and the accuracy of the model is calculated using the predicted data. This is the model accuracy. Now in this model we are predicting the age. The test data on the training model gives a training accuracy of approximately 26%. This is called the model accuracy. Now again in the same code we load the trained data and test the model on the test data. This is called the same model. So this is the same model accuracy, which is which is also the same as the model accuracy. You see that the accuracy is very low. This is because of the randomness of the data set. Next we look at the clustering. Since we have a huge age group, we have scope to cluster different age groups together and form groups. In this project, a basic clustering was done using k-means algorithm. Since the objects for the k-means clustering need to be numerical features, only the year, month and the age fields are used for this model. Each object can be thought of as being represented by some feature vector in an n-dimensional space, n being the number of all features used to describe the objects to cluster. The algorithm randomly chooses k points in that vector space where these points serve as the initial center of the clusters. After this, the objects are all assigned to the center of the cluster they are closest to. For each iteration, a new center for the cluster is computed by averaging the feature vectors of all objects assigned to it. This complete process is repeated, iterated over and over again till all the points converge after a finite number of iterations. Initially, the model was trained to create 2 clusters over a maximum of 10 iterations to create the model, as given here. This k value gives the number of clusters. So the data is loaded, parsed, and then this is the clusters which are created after training, and then you find the error, which is called the within set sum of squared error. So we have 2 clusters, 10 iterations each, and we find that the WSSSE error is 1.01 billion. It's extremely huge. However, now we run the same model for creating 15 clusters over a iteration, 30 iterations and 10 runs. So we computed the same model for 15 clusters, and you observe that the WSSE has gone down to 3.9 into 10 power 7. It's gone down over 10 times. So as you can observe, the WSSE reduces from a billion to 10 power 7 as we increase the number of clusters to be created by the algorithm. However, large the number of clusters created, the error is still huge. This is due to the scattered manner of the data set, and also because there is no interdependence between the fields which are used here. Now we have run 2 different kinds of methods. One is classification, another is clustering. Now we look into the results we get from the classification. So what we have done till now is the models are ready to predict the data. Since we got a data set which has only a few number of fields which can be used for classification, which can be correctly used for classification, it was difficult to get any interesting results out of it. However, all the models are ready to predict whichever data set is given to them. Now if there is interdependencies between the fields, the model is prepared to give good results. Then the data has been manipulated suitable to predict. We have also given the data type which should be given to the model so that it can predict as required. As explained multiple times before, due to this random data, we find that the accuracy is very low and there are high errors. And also one more reason why the accuracy and the errors are bad is because there is no interdependence between different fields coming in. Basically, for the age grouping, we have used clustering. We used the k-means algorithm alone. So we found that we still get a very high within set sum of squared error, still owing to the fact of the randomness of the data. However, increasing the number of clusters, the value of k, can lower the WSSSE.
To sum up, initially we did analysis of New York State traffic violations from 2012 to 2015, and the most important results were aggressive driving behavior that is signified by top types of violations, very high percentage of young people including the dataset, speeding as top violation type, and reduction of mobile phone violations. As far as the prediction part is concerned, due to the randomness of the data and low interdependencies between the columns, we got low accuracies and high errors. In order to be able to predict results, there must be some sort of a connection between the columns. Our suggestions for the state of New York are educational programs to establish proper driving attitude, especially for young people in high schools and colleges. Also, increase speeding fines with new surveillance technologies as a support. Finally, it is imperative to reduce aggressive driving behavior by enforcing stricter tests to obtain a driver's license. In other words, not everyone is eligible for driving. As far as future work is concerned, we definitely would like to use our algorithms on different dataset. We can obtain a dataset with interconnected columns even if it is smaller than 1 gigabyte. We would like to do even more impressive visualization and extend our work beyond US borders. At this point, we would like to thank our professor Jing-Hyun Lim for the opportunity to take part in Big Data Analytics class and learn so much out of it. Also, RTAs, especially Mr. Eric Johnson and Mr. Gautam Sihag. If you have any questions, please feel free to contact us. Thanks for watching, everybody.